Okay, so the plan for today is just to cover the comparison tests in 11.4. So we've looked at convergence of a series in general. Uh, we looked at some special cases like geometric series or harmonic series. We also talked about the test for divergence. And then last time we talked about the integral test, where we kind of roughly speaking said that a series converges if and only if uh, a related integral converges. And today we're going to continue on with that with a couple more tests, the comparison test, the direct and the limit comparison test. The quote of the day today is by philosopher David Hume: "A wise man always apportions his belief to the evidence." Um, so in my stats class, we're moving from kind of the more theoretical side of things to the more inferential side of things. And that's really kind of what this is geared toward, but I think it does apply to really kind of any scientific field that we might want to go into. And I think maybe related to that idea is also from Hume, the idea of Hume's guillotine, that science and stats and technical fields are pretty good at making is statements. So saying what is true about the world, but it's not really in our ballpark to make ought statements. So saying, what goals uh, we ought to kind of set for ourselves. Maybe that's a question for, as I often say, like pastors and philosophers. Um, our lane is to evaluate is statements. Can we understand the world better so that when we decide what our terminal goals are, we can come up with better instrumental goals and better progressions towards those terminal goals. Okay, so moving on to the comparison tests. Oh, and as an aside, I posted just this morning one supplement for some of the material in sequences and so on. And then I'm going to post an additional supplement on some of the applications of geometric and harmonic series that I had mentioned before. So that'll be the supplement for this week. And we are actually a little bit ahead of schedule. The comparison tests weren't originally slated to be covered until next class, but because chapter 11 is such a big chapter, and we're right up against finals week at the end of chapter 11, I think it's good to have just that little bit of buffer. So, so moving on to the comparison tests. We have two theorems, the direct comparison test and the limit comparison test. They're somewhat similar in nature, and both of them have this general idea. They both feel a little bit like the integral test, actually, where we're saying this series converges if and only if this kind of related integral converges. But here, instead of comparing a series with the related integral, we're comparing a series with another related series. So maybe we have a series like, say, this one here that we don't know a whole lot about. I haven't seen the series sum 1 over n cubed plus 10 before, but maybe I can somehow relate that to a series that I do know about, maybe the harmonic series, or maybe a geometric series, or maybe a p series. If I can relate the series under consideration to a series that I know more about, maybe I could use my knowledge about that other series to help answer the question of whether the initial series converges or diverges. So that's the idea behind both of these tests. The direct comparison test requires that two series are positive series, so some an and some bn are positive series. What we mean by that is that each of the terms in both series are positive, or at the very least that for each series, after a certain point, all terms are positive, right? Series convergence is really a question about the tails. So it's not such a big deal if, the first couple of terms or, even the first 100 or 1,000 terms don't satisfy some criterion. As long as we can satisfy that criterion once we're so far into the tail, then we're good. So if we have two positive series, then we can say the following. If an less than or equal to bn, so if each term of the an series is less than or equal to the bn series term, and some bn converges, then some an converges. this has a very much like a squeeze theorem feel, right? That like if the AN terms are stuck between 0, obviously, because they're positive series, and BN, and some BN converges, the individual terms in the B series must get small enough fast enough to converge. And since the AN terms are stuck between the BN terms and 0, they must also get small enough fast enough to converge. That's essentially the argument here. Obviously not a full proof, but that's just giving you kind of a rough idea. And on the other hand, we can say that if AN bigger than or equal to BN and some BN diverges, then some AN diverges. The limit comparison test. So one of the challenges with a direct comparison test is establishing an inequality like this that can sometimes be difficult to do. The limit comparison test can sometimes be nicer. Here we again have the criteria or the assumption that if AN and BN are positive series, and we also have this additional criterion that if the limit as n goes to infinity of AN over BN equals L, a real number, so that limit's not infinity, then some AN and some BN either both converge or diverge. So what we're saying is if they, and this should be L and R plus, a positive real number. Sorry about that. But what we're saying is that in this case, if in the tails, if the limit is of AN over BN is a positive real number L, then what we're saying is that basically AN and BN kind of behave the same way in the tails. And because convergence is really a question about the tails, then under those criteria, this one and this one, then they either both converge or both diverge. So practically speaking, how do we use these theorems? Well, let's say that we have some AN that we're interested in, and we want to know whether it converges or diverges. If we can come up with a sum BN, whose convergence or divergence properties we know, and we can link the two series with one of these comparison tests, then we might be able to use this theorem along with the knowledge about the some BN series convergence or divergence properties to make a claim about the convergence or divergence of some AN. So practically what that looks like is something like this. We have this series that we're interested in. Sum n equals 1 to infinity of 1 over n cubed plus 10. We want to show that it converges. Let's show it by direct comparison. So I might say something like consider, so let's call this AN. So let's consider some n equals 1 to infinity of 1 over n cubed. So we'll call this some Bn. I note that these are both positive series. All of the terms in the AN and the BN series are positive, so that's good. And I also note that AN equals 1 over n cubed plus 10 is less than 1 over n cubed, or Bn. If I make the denominator larger, that makes the whole fraction smaller. So no problems there. And now I can say by, and I need one more thing. I know that some 1 over n cubed converges. It's a P series with P bigger than 1. So by the direct comparison test, I have positive series. I have an less than or equal to bn, and some bn converges. Some an must converge. So I came up with the series that I wanted to use for the comparison. And that's the kind of the challenging part of using these comparison tests, is coming up with the right series that has, it kind of walks this tightrope sometimes between, I need it to be a series that is simple enough that I know its convergence or divergence properties, but it also has to be kind of close enough to the complicated series that I can make the comparison, whether it's the direct or limit comparison. So it needs to be similar to the series under consideration, but similar enough that I can make the comparison, but hopefully simpler than it so that I can use my prior knowledge. What about this one? Very similar problem. Sum n equals 1 to infinity of 1 over n cubed minus 10 instead of plus 10. Unfortunately, here a direct comparison, the same direct comparison as above doesn't work. And the problem is that if I tried to do the same thing, an would be just a tad bigger than bn. Do I really think this minus 10 actually, qualitatively changes the problem? Not really. I mean, I think, again, we're thinking of convergence being a characteristic of the tails when n is very large. When n is very large, n cubed is huge. That plus or minus 10 pretty much doesn't do anything. It's negligible. But I still can't just make the direct comparison with 1 over n cubed. I might be able to make a comparison with something like 1 over n squared. I could probably make an argument there. I would have to do quite a bit of work, though, to figure out for which n's is 1 over n squared bigger than 1 over n cubed minus 10. And right, that seems like it's quite a bit of work. So there's enough room in some sense between things that I know converge, like 1 over n cubed or 1 over n squared, and things that I know diverge, like the harmonic series, that I probably could find a direct comparison here. But it's, at the very least, it's going to be messy. But really my thought here is, well, for large n, this minus 10 is pretty negligible. This basically just looks like 1 over n cubed. I would still like to do a comparison with 1 over n cubed, but a direct comparison, again, just the details of the algebra don't work out so nicely here. But could I do a limit comparison? Yeah, I think a limit comparison would work. Basically, I'm saying in the tails, 1 over n cubed and 1 over n cubed minus 10 basically look the same. So let's again consider some bn equals some 1 over n cubed. And again, we know this converges. And if we call these the ANs, we know that these are both positive series. Well, the ANs, I guess, are negative for a couple of terms, n equals 1 or n equals 2 terms, but for n bigger or equal to 3, these are definitely both positive series. Again, if I have a couple of terms at the beginning that don't fit in with the assumptions, I could really, if I wanted to be super pedantic, I could split off those first couple of terms separately, have 1 over 1 cubed minus 10 plus 1 over 2 cubed minus 10 plus, and then the series. And then I could argue that the series consists of all positive terms. But here we're just glossing over that detail a little bit. These are both positive series for n bigger than or equal to 3. And again, my direct comparison isn't going to work nicely. I want to use a limit comparison. So what do I have to show? I have to show limit an over bn is a positive real number. So what's an over bn? That's 1 over n cubed minus 10 for an, and then 1 over bn is n cubed, like that. And I can pretty clearly see this limit is going to be 1. I could divide top and bottom by n cubed. That 10 over n cubed just goes away, and I get 1 over 1. This is 1, which is indeed a positive real number. And now I can say, by the limit comparison test, since some bn converges, then some an converges as well. So sometimes direct comparison is nice whenever it's easy to get an inequality. When things are a little fuzzier, when we say, okay, this looks like 1 over n cubed, but coming up with that inequality is going to be messy, a limit comparison might be nicer. Okay, let's evaluate the convergence of sum n equals 1 to infinity of log n over root n. If we try to think of a limit comparison here, this might be kind of a hard limit comparison to really evaluate. It might be hard to come up with another series to use for a limit comparison test. I think we probably could, but it might be a bit of a challenge. But one thing that I kind of realize is, well, if I think of this 1 over root n, some 1 over root n diverges, right? This is a p series with p less than 1. It diverges. What effect does log n have on this? Well, log n in the numerator just makes it worse. It just makes the individual terms even bigger. So the log n's contribution just, in a sense, makes it even worse. Now, we might be tempted to use, say, test for divergence, but note that log n over root n does go to 0. So the test for divergence, or the divergence criterion as it's sometimes called, doesn't immediately say that we diverge. We might converge, we might diverge. But based on what we said over here, I think this is still going to diverge. The terms go to 0, but I don't think they go to 0 fast enough for convergence. I think it's kind of like a harmonic series where the terms go to 0, but they don't get small enough fast enough. And again, I might be able to find another series to use a limit comparison with, but I can't limit compare with 1 over root n, because in that case, when I take the ratio, the root n's cancel out and log n shoots off to infinity. It's not a real numbered limit. Now, I think, it wouldn't be a bad exercise to try to find a series that you can limit compare to. I think with a little bit of thought, you could find one. But here we're going to use direct comparison test. So we're going to consider some bn, sum of 1 over root n equals 1 to infinity. We know this diverges by a p series with p less than 1. So this up here was just kind of scratch work. But now we're getting into the actual proof. We know that log n is positive for n bigger than 1, and root n is positive. So these are both positive series. And I also know that log n is what? It's going to be greater than 1 for n bigger than e, or n bigger than or equal to 3. So, whoops, an bigger than or equal to bn, at least for n bigger than or equal to 3 anyway. So we have positive series. We have an bigger than or equal to bn, and we have that some bn diverges. So we can say by the direct comparison test, since some bn diverges, some an diverges. And I don't know if I actually said it, but these are the ANs. Any questions so far? So similar to, say, the test for divergence or the divergence criterion, similar to, say, the integral test, this these arguments don't tell us what the sum of the series is when it converges. We're just evaluating whether the series converges or diverges. So it's somewhat abstract, right? We'll see a little bit later that we will have some methods for approximating the values of convergent series. I mean, obviously, one method is just to use the computer and add up a whole bunch of terms of the series and see what number you kind of get close to. But if you're going to search for the sum of the series, it's good to know at least that it converges first. It's good to know that a sum exists before you start trying to find it numerically. Otherwise, you can kind of get into trouble sometimes. And this will also be an important idea later on when we talk about things like Taylor's theorem and things like that. These ideas of convergence are very important in those contexts as well. So it might seem all a little bit abstract at this point that we say some an converges and just kind of leave it there. And maybe it feels like we should drive it home and say, okay, some an equals 5. But it turns out that that's usually a fairly difficult thing to do for non-trivial series. For things like geometric series, that's really kind of the standout where you can come up with the sum, explicitly, maybe for some things like some telescoping series and so on. But for series like this, it's not very easy to do. Okay. Okay, example 4. Let's try to prove this following statement. If we have a series, sum n equals 1 to infinity of an, that converges, and if there exists a big N such that an is in the open interval 0 to 1 for all little n bigger than or equal to big N, then the sum of the squared terms also converges. So if a series converges, if far enough out into the tail, all of the terms are strictly between 0 and 1, then the sum of the squares converges as well. Let's prove that. So what do we know? We know some an converges and that an is in 0 to 1, open for n bigger than or equal to capital N. So we can say let bn equals an squared. But note that if we square a number between 0 and 1, it gets smaller. So bn is less than an. But we also note that bn is positive and an is positive for n bigger than or equal to capital N. So these are positive series. So we have two positive series. And I have this naturally occurring inequality. I can say by the direct comparison test, since Bn less than An and some An converges, then some Bn must converge. Some Bn or sum of An squared converges. Any questions so far? So direct comparison tests seem to work a little better here. And if you wanted to, you could try to see if limit comparison tests would work here. So when I'm going through and I choose to do one of these one way, as you're going back through your notes, maybe ask yourself, would the other limit versus direct work as well? Could you make it work? Is it going to be overly messy to make it work? Is there a reason I chose one over the other? So those might be good questions to ask in this section. All right, so example 5, we're actually making much better time than I thought we were going to. Example 5, evaluate the convergence of this series. Sum n equals 1 to infinity of n over n squared plus 1. Now here's where a kind of gut feeling comes into play, right? I want to start out by thinking, do I think this is going to converge or diverge? And again, I know that convergence and divergence is a question of the tails. So when n is large, what do the individual terms kind of look like? So for n large, well, the plus 1, that basically has no effect, right? If I have n is a million squared plus 1 is basically the same as a million squared. So for n large, this basically looks like n over n squared, or 1 over n. This really seems like a harmonic series. Now I could maybe try a direct comparison with a harmonic series, but my denominator is just a tiny bit bigger than a harmonic series, which means my individual terms are just a tiny bit smaller than the harmonic series. But if I wanted to compare to the harmonic series and show this diverges, I would need my terms to be bigger than the harmonic series terms. So I think I'm kind of naturally, at least, just on the wrong side of the harmonic series to use a direct comparison here. Again, maybe there's enough room, so to speak, there that I could come up with some other function to compare against. Maybe I could, but I think a limit comparison is going to work a lot better here. So let's consider Bn, some Bn, the harmonic series. This diverges. As it's the harmonic series, it's a p series with p equal to 1. Again, I don't want to do a direct comparison, but I would like to do a limit comparison instead. I think that'll work better here. The limit comparison really doesn't care about these little nuanced details nearly as much as a direct comparison. I see that these are both, and we're going to call these AN, these are both positive series. As an aside, if they were both negative series, I could just take their negatives, show that they diverge, and then that would make the same claim about the original series. So these are both positive series. And we have that limit n goes to infinity of an over bn is limit n goes to infinity of an is n over n squared plus 1. And then 1 over bn puts another power of n up top. And again, I could divide top and bottom by n squared. The 1 over n squared goes away, and I get 1, which is a positive real number. And I can say by the limit comparison test, since some bn diverges, some an must also diverge. So here I've concluded that some an diverges, and I've also proved it. Some of the problems in the homework will kind of walk you through a proof, but some of the problems will just ask you, does it converge or diverge? And for those problems, I'd recommend for the homework, when you go through and you have to pick converges or diverges, get a gut feeling and then try to prove it, just as an exercise, just to make sure that you're right. For an exam, if it's just converges or diverges, do as much work as you need to convince yourself that your answer is right, and then move on. So for an exam, if it just asks, does this series converge or diverge? I'm expecting you to look at it and say, okay, I mean, this feels like a harmonic series. Okay, I could use a limit comparison there, and that would work out. You don't have to write out all the details, right? So go through just enough to convince yourself, in this case, that it diverges, and then just pick diverges and move on. So when I evaluate the time that I expect you to spend on a problem like that, it's not, I'm not taking into account writing out the full formal proof. But in the homework, I think that is a good thing to do, is to go through carefully and prove these things, so that you're able to if you needed to. Okay, and then problem 6. So evaluate the convergence of this series, sum n equals 1 to infinity of 1 over log n plus n. So again, I look at this and I say, okay, for large n, I know that n grows much faster than log n, right? In other words, I know that n over log n as n goes to infinity, that's infinity, right? Or log n over n goes to 0. So I know that, kind of roughly speaking, n grows much faster than log n. So I'm kind of thinking that this is going to end up pretty much just looking like 1 over n in the tail. I'm thinking that it's going to pretty much just look like a harmonic series. If I wanted to direct compare to a harmonic series, the problem is that my denominator, I don't know why this n is not italicized, but if I look at this denominator, it's just a little bit more than the harmonic series denominator. Or the size of each of these terms is just a little smaller than the harmonic series terms. If I think this looks like the harmonic series, I'm trying to show it diverges. So if I wanted to compare it to harmonic series, I would need to show that these terms are bigger than the harmonic series terms. I'm on the wrong side for a direct comparison. If this was something like 1 over n minus log n, great, a direct comparison would work just fine. But again, here, I'm going to use a limit comparison. With the harmonic series. I know this diverges as it's the harmonic series. I see that both of these are positive series. And what's the limit of the ratio? So AN is 1 over log n plus n, and 1 over Bn puts an n up top. And here I might have to do a little extra work. I divide top and bottom by n. And now my question is, what's the limit n goes to infinity of log n over n? I know that that's 0. If I wasn't sure of that, I could move into the x world, use L'Hopital's, make that argument, and then be satisfied with that. But I see that this is, 1, a positive real number. So my second criterion to use the limit comparison test also holds. We have positive series, and the limit of the ratio being a positive real number. So I can say by the limit comparison test, and these are my ANs, since some BN diverges, then some AN diverges. So again, a couple things with the series, especially when we're just given a series and told to evaluate its convergence. We want to do something, find some way to get a gut feeling, right? As n gets large, what's happening? What are the dominant terms? Or what are the dominant pieces of these terms? I see that the n kind of dominates the log n, or the n squared dominates the 1, but doesn't really dominate the n, right? This kind of n over n squared, they're in a bit of a battle. The root n up here dominates the log n. So what are the, as I move into the tails, what are the most important pieces in my terms? And that lets me simplify things a little bit and make a guess. In this case, I'm guessing that this is going to diverge because I think that it's going to kind of look like or kind of act like the harmonic series in the tails. And then I have to figure out, okay, what's my strategy to actually prove that? So when I get an idea of how I think it's going to behave, and then I have to find a series to compare it with and decide whether I'm using a direct comparison or limit comparison. All right, any questions on the comparison tests? So these tests are pretty useful, and we'll also see kind of similar tests that are that have a similar feel a little bit later on in this chapter.